So, this is the lecture 6 where we will talk about force vibration of single degree of freedom system. So, all these days we have been talking about free vibration where the force was 0 or there was no externally applied force, but in from today onwards, from this lecture onwards, we will be talking about system where an externally applied load is acting, and we will see what are the different forms of loading that can be experienced by a structure under real life condition, as well as we will see how to analyze the system because of various forms of loading and understand what would be the response of the system or a single degree of freedom under different kinds of loading. So, let us first go to this slide where I have just given a small introduction of on what kind of loads a structure can experience. So, we will be considering the same old single degree of freedom system, a simple spring mass damper system. What is different from what we have done earlier to what we will be doing henceforth is that all this while we have considered that this externally applied force, was 0. So, that is what we had assumed in all this while. Okay. This was 0 and the vibration happened due to initial excitation, initial displacement and or initial velocity. But hence now onwards we will consider systems where there would be a non-zero external force. So, we will no longer have force equal to 0 and we will move into non-zero external forces. So, therefore, there would be a slight change in the equation of motion. So, previously if we look from a mathematical perspective, previously we had a homogeneous differential equation, okay, where the right hand side of the equation was 0. From now onwards, we will not have a homogeneous equation, rather there would be some force term on the right hand side, and this force is going to be a function of time. It is not going to be a static force, what you have learned in your solid mechanics or engineering mechanics or structural mechanics, but in dynamics this force is no longer a static force or a force that does not change with time. Here we will deal with forces that changes, the amplitude or magnitude of the force changes with time instant t. Okay. So, let us briefly talk about what are the various forms, some of the forms of force that can act on a structure. The first thing that can act is a wind load. Okay. So, wind load, all these tall buildings, okay, the bridges, they all experience wind load and the structure needs to be designed for such wind loads. Okay. Another new problem that we have to tackle, a new problem that is coming up and which is getting a lot of interest from the structural dynamics people, is the problem of windmills. The windmills that are there in several countries all over the world to generate alternate power from the wind energy experience a huge amount of wind load, because they are very tall structure, and we also need to. So, this is becoming a challenge where we need to design these windmills which are undergoing wind load. Okay. The next common form of load is live load. By live load, we understand the load that is experienced by a structure due to, say, traffic movement, due to movement of vehicles, due to several machineries that are hosted on a structure. So, all these forms of load is called live load. This is very commonly experienced by any of the civil infrastructure. Okay. The third important load where people are much interested in is the seismic load. Okay. So, we all know what is seismic load. I mean, we all know how catastrophic an earthquake can be to a structure, to a building, a bridge or any other infrastructure. And so, there is a special topic of structural dynamics which is called earthquake engineering, where people study the response of a structure and analyze the response of a structure due to such earthquake loading or seismic loading. So, there is a separate course, separate branch of engineering which is called earthquake engineering. The other load that also one is an important class of load is the oceanic or tidal load. So, with this recent catastrophe happening due to tsunamis and all, we are very much aware how what could be the magnitude of this tidal or seismic load as tidal or oceanic load. So, understanding this oceanic load and tidal load becomes very important when you are trying to design an offshore structure like the oil rigs that are placed offshore, and building, I mean designing dams and barrages where we need to understand the tidal load. The fifth kind of load is the blast or impact load. This is very commonly experienced in aircraft, which under certain conditions where there is a bird hit, there is a gust, sudden change in wind, or there is a tool drop. Okay. So, we will as of now not differentiate between this kind of load. So, we will just have in mind that these are the different forms of loading that the structure can encounter. Now, a load can also be differentiated into two major classes. One is called the deterministic loading, another is called the non-deterministic or random loading. So, what happens in deterministic loading is that the load or the force is known beforehand. So, I can say that the load that is going to come at 5 seconds beforehand. I can say at 4.9 seconds what is going to be the load at 5 seconds, or the magnitude of the load is known beforehand to me. Okay. And in non-deterministic load, we actually do not know what would be the load at a future time instant. Especially, so a classical example of non-deterministic load is the seismic load or earthquake load. We really do not know at the next time instant what is going to be the amplitude of the load. So, this kind of load is called non-deterministic load, and analyzing vibration or dynamics of a structure under non-deterministic load is falls again under a special class of vibration called random vibration. So, there are separate courses for understanding and analyzing random vibration of a structure. So, in this course we will be only focused towards deterministic load. We will not be dealing with non-deterministic load. So, this course we are only going to deal with deterministic load. This course will deal only with deterministic load. The loads or the force which are known beforehand to. The entire force history or load history with respect to time is known to me. So, with this introduction, let me move on to the next topic. So, most common form, I can say this, that the most common form of loading is harmonic loading, where the excitation load or the externally applied load is an harmonic function of time. It is either cosine or sine with certain frequency. Okay. So, this is the equation of motion of such a loading, where the load, the externally applied load f t is nothing but a constant c into cos omega t. okay, where C is the amplitude or magnitude of the load and omega is the driving frequency. So, this omega is the driving frequency or frequency of the forcing function. Now, what happens is that what I have done is that I have replaced C, which is the amplitude of the force, by K into A, where K is nothing but the spring constant. It is the spring constant or the stiffness of the system. So, the stiffness of this single degree of freedom system is K, which is the spring constant of the system. So, this is the stiffness of the system. Okay. And A is again a constant, which is nothing but the amplitude of the force C by the spring constant K. This is a small mathematical manipulation that I have done, which will be very useful later. So, right now let us not bother much about why I did this small mathematical manipulation here, but we will get to know why we did it at the later stage. Okay. So, if this is the equation of motion, so I see that my right hand side of the equation is no longer 0 and therefore, my equation is a non-homogeneous equation. So, we know how to solve a non-homogeneous equation. So, I mean this is there in basic engineering mathematics, that the ways to solve a non-homogeneous equation. So, when we have a non-homogeneous ordinary differential equation, the total solution u t, okay, is always equal to the complementary solution, which I call u c t, and the particular solution, which I call u p t. So, u c t is nothing but the, so this is the total response, u c t is the complementary solution and u p t is the particular solution. So, we all know that u c t or the complementary solution is nothing but the solution of the ordinary differential equation, considering it to be homogeneous, considering that the right hand side is equal to 0. Okay. So, most of us are aware of this kind of solution. So, let us now try to find out what is going to be u c t and what is going to be u p t for this particular case. Okay. So, u c t is going to be, so let me first write this equation in the conventional form that we have been doing all this time. Okay. So, I write it as u double dot, then c by m, which is 2 zeta into omega n is the natural frequency, into u dot t plus omega n square into u, and that is equal to k by m, which is again nothing but omega n square into a cos omega t. This is what we get by writing this equation. So, what is u c t? U c t is nothing but the solution of the homogeneous part of the equation. So, it is the solution u dot t plus omega n square u equal to 0. The solution of this is u c t. Okay. We have already found out the solution u c t in the earlier lectures. So, let me just directly write the form of u c t. So, u c t is nothing but e to the power minus zeta omega n t, okay, into C 1 plus C 2 into cos omega n t plus I C 1 minus C 2 into sine omega n t. This I have already found out in the previous lectures. Okay. Now, what is the nature of this response? What is the nature of this solution? As I said earlier, that the solution of this is going to be a sinusoid with exponentially decreasing amplitude. Now, because this will give a sinusoidal response, this is going to be a exponentially decreasing amplitude. Now, since this solution is a sinusoidal function with exponentially decaying amplitude, this solution is going to become 0 or very close to 0 after certain time, after elapse of certain time. Therefore, this solution, when we are trying to solve force vibration problem, this solution is called the transient response. Because this solution is going to become 0 after some time, 0 or very close to 0, I mean almost equal to 0 after some instance of time. So, therefore, this is called the transient response. We can, as we have done earlier, C1 and C2 can be found out from the initial condition. Now comes UP. Now comes the particular solution. Now let us try to find out the particular solution. So, we have found out the complementary solution. Let us try to find out the particular solution. So, we all know how to solve UPT. So, our next job is to find out UPT. So, we have all seen or know how to find out the particular solution of a ordinary differential equation. So, in this I will not get into details of it. If you want to revisit it, you can always follow any higher engineering mathematics book. So, let me assume that UPT is going to be x cos omega t minus phi, where x is unknown, phi is unknown. I do not know x, this is not known, this is also not known to me as of now. And omega is nothing but the driving frequency or frequency of the external load. Okay. So, now what do I do is that, so we all know that the particular solution should be a solution of this differential equation. So, in order to see, so we have assumed this solution, right. So, this is the assumption that we have. This is the solution that we have assumed. So, what do we do to find out x and phi? We plug this into this equation and see for what value of x and phi this assumed solution is going to be a solution of this equation. If we can find that, then we can find out the particular solution of the system. Okay. So, let me just try to find that out. So, what I am going to do is I am going to plug this solution into this equation and solve for x and phi. Okay. So, UPT is going to be x cos omega t minus phi, and the equation of motion that I have is 2 zeta omega n u dot plus omega n square u is equal to omega n square into A into cos omega t. Okay. And I have to plug this in here. If I do so, what am I going to get? I am going to get minus omega square x cos omega t minus phi. Okay. Then I have minus 2 zeta omega n into omega into x into sine omega t minus phi, and then I have omega n square into x cos omega t minus phi, and that is equal to omega n square A into cos omega t. Okay. So, let me just rearrange this. I am trying to rearrange this and write this as omega n square minus omega square into x into cos omega t minus phi, okay, minus 2 zeta omega n into omega into x sine omega t minus phi is equal to omega n square into A cos omega t. Okay. So, what I will again rearrange this and write this as x into. So, in place of cos omega t cos phi, I can write this as omega n square minus omega square cos omega t into sin phi plus omega n square minus omega square into sin omega t into cos phi. Sorry, I just did a mistake. So, this is going to be cos phi sin omega t sin phi minus 2 zeta omega n into omega into sin omega t sin phi minus 2 zeta omega n into omega cos omega t cos phi into sin phi equals to omega n square A into cos omega t, and this is going to be plus. Okay. So, let me again write this term in terms of omega n square minus omega square into cos phi plus 2 zeta omega n into omega into sin phi into cos omega t plus x into omega n square minus omega square sin phi minus 2 zeta omega n into omega into cos phi into sine omega t is equal to omega n square into a cos omega t. Okay. So, let me just check if I have done it correctly. Yes. Yes. So, now if I equate the right hand side with the terms in the left hand side, from this equation I can actually get two equations. The first equation being omega n square minus omega square into cos phi plus 2 zeta omega n into omega into sin phi is equal to omega n square into a. So, what I have done is that I have equated the terms corresponding to cos omega t with the terms associated with cos omega t on the right hand side. So, that gives me my equation 1, and I also equate the other terms which are associated with sin omega t with that in the right hand side. So, there is no sin omega t in the right hand side, therefore, I can write this as omega n square minus omega square into sin phi minus 2 zeta omega n into omega into cos phi is equal to 0. So, this is my second equation. Okay. So, if I use these two equations and if I try to solve for x and phi, which is very easily doable, right. I have to just square this equation, add these two up, that should lead me to the value of x, and the value of phi can be obtained from equation 2. So, I have, let me just check if I have done it correctly. So, this is the equation that we get. So, now our job is to solve these two equations and get the value of x and phi. So, let me just try to do that. If I do that, I will let me just write it down. So, if I do that, I will be able to solve x and I will be able to solve phi. Okay. So, in the next lecture, I will be talking about what would be the value of x and phi, and we will see how to analyze this x and phi. Thank you.